Hi. So this is gonna be the first of series of tutorials on how to use the following codes we've been training on for generating molecular dynamics data for binary alloys and bearing composition and how to do all the post processing and calculations that come after it. So I'm gonna start here on the GitHub we have with all the codes, and then the first thing we need to do is to download and run the code that generates all the data for that actually runs the simulations. And and for that, so we go to simulation data generation, and then I'm gonna go with disorder just because it's easier. That I can do a more specific one for order in the future. But yeah, I'm just gonna go with disorder script, then download the thing. Should be completed, and then we go to downloads. It's here. And then we take it to whatever folder we're gonna be using. In this case, I have a folder for this tutorial here. Paste it. Now we open a spider or whatever IDE. This might just take a couple of seconds to open. Okay, so we have now spider open here, and so next thing we're gonna do is to go to the folder where I pasted this script, this Python script, and then we're gonna open it. And then on each of these codes, you have all the documentation here, like for like a better description on what each of these does, and then also like our emails, mine and Jorge's one, Dr. Muñoz. And so the first thing we're gonna see is that it asks us for a file directory, and what this means is that it's a directory where we're gonna store the potential and the LAMMPS input file we're gonna send to the terminals. So once you have it open here, the next thing we're gonna do is go back to a GitHub folder, and then I'm gonna go back home and get potentials and input files and download these three things here. I guess by one. Iron vanadium library meme, iron vanadium meme, and iron vanadium external positions input file. In this case, for this system, we are using iron vanadium, right? But this is just any potential for lamps. In this case, I mean potential, and this is required by the simulation to run. And then I'm gonna go here and then bring this back. And now, so the file directory we need here is whatever file directory these things are on. In this case, actually getting like a nice like way to get it like from other directories is not necessary because I'm pasting it like right here. But let's say that you want to keep like your input, your potentials, and your input in a separate folder, like somewhere else in your system. So the only thing you need to do is get the directory of whatever this is, right? And then if this is Windows, just need to replace the forward dash thing for regular ones for a Linux reason. I don't know. For Windows, right? I think for Mac, you're just gonna have like the regular slash, the one I'm replacing for. Okay, so now we have that. We're gonna move on here, and then the only thing that's usually really changed on this code is this parameter here, the vanadium composition, which in this case I'm gonna leave at zero point 0.5, but it can be all the way from 0 to 1, or I don't know, 0.75 or something, right? Then something else that can be changed as needed is the lattice parameter value in Armstrongs, that where you start the simulations, and then how many simulations you actually run. In this case, this goes all the way to 3.2 Armstrongs, so it simulates all those different lattice parameters and values, and then it finds the minimum spot, right, for it to find like what's the actual lattice parameter value. Okay, so now we have this. I just want to check one thing on the input file in this case. These two files, if it is the same system you're simulating, which most likely will not be, but those are never like really changed. But in this case, something that is usually changed on a LAMMPS input file, and what can be changed is the temperature you want the thing to be simulated. For example, in this case, is 1300 Kelvin. So in case you want to make a 1300 Kelvin, you'll just change these three values over here, and then you also have like the run parameter, how many the thermal value, which is like how many time steps you get like a printing of energy and step, and you're also gonna get like your dump files and everything. But this is like more detail in a lamp simple file can be covered somewhere else. But if you want to change the temperature of the thing only, you will need to change these three parameters, which in this case I did, right. Then I'm gonna close this, and then I'm gonna run it. You're gonna see how the different the code actually creates directories for each of the lattice parameters you're gonna be using, right? From 2.8 as in the code to 3.2, we're gonna see in a moment. So what's gonna happen now is that each the computer is gonna run all the calculations. It's gonna run a calculation for the system in 2.8 Armstrongs, and then 2.81 Armstrongs, 2.82 Armstrongs, and at the end you're gonna get an lattice parameter versus energy curve, so you can actually determine like what's the predicted lower energy value for the simulation, what's the actually predicted one, which we're gonna see in a moment. 3.19, 3.19, that's a final value, yeah, because if it was 3.40, 3.2 will need 41, okay, including 2.8. So the as of this point, the code itself is finished running, but we're gonna see that's not really the case for all amps, because basically what the code does is the code itself just creates the directories, it copies the potentials to each of them, and sends the simulations to the terminal with this line over here. And I've been seeing that some people get troubles with newer LAMMPS or Mac, for example, that they actually need to change this command. But that's the only thing we will really need to change. What I expect that it will be needed to change. I think in Mac is something like LMP serial, something like that. But so the code basically sent all the simulations needed to send to the terminal, and now it's up to the computer to finish it running, right? And we're gonna see how. Should take like 5 minutes, let's say. And it's getting slow, like you can see Python is occupying memory and everything. Okay, so I gave it like 5 minutes, let's say something like that. And now everything finished running. And and like CPU usage is pretty low or back to normal. So I'm gonna go back to the folders, the simulations, and we're gonna see how like in each of these folders you're gonna have the potential files, the input file, these atoms positions dot data file that actually creates the atom positions. So this gets this is an output from the code directly. So you don't create the atoms as normal as in the input file to lamps. You create them externally and then you import that to the input file, which we can cover later with more detail in the tutorial. But it's one of the main things the code actually does. And then we have this log lamps file, which is like a transcription of everything that went into the terminal and how it actually would look like in if you run it like manually. And and so what this is gonna give is that it's gonna have here the energy values, the total energy values that we have, and 500 time step and 1000 time step, which is how we are running it here. But these are the two values we need actually, these two. And we're also gonna get here to see how the total wall time, how much time it took to run, right? And it was 4 minutes and 52 seconds in this case. And so we're gonna have like in each of these, we're gonna have once everything finished running, we're gonna have it completed in all of them. In this case, the last one is also completed for 4 minutes and 12 seconds. And but yeah, basically at this point we are done with data generation. We have all the data we need. Like starting from here, it is post processing only. The data itself it's over. At least if it is like a simple simulation here, like in this case and something, right? But yeah, everything else will be covered in the next tutorials.